61. Okay, so we are looking at inverses, and inverses, again, like a lot of what we've done, not very new to you, but we get very specific with the language here, which is going to be different than the language you have probably used with it. This is one of the one of the explanations on an FRQ, which they were very, very specific about what they were going to accept and what they weren't going to accept. So we'll talk about that when we get there, and then we're going to practice that a lot. All right, so what we know already about inverses, and this is titled inverse functions, but it starts talking about inverse relations, because remember, not everything is a function. You need to do some jumping jacks? No, you're good. Okay. Not everything is a function, so if it's not a function, it's just considered a relation. But an inverse will undo a given relation, just like addition and subtraction are inverses of each other. I add 3, then I subtract 3. I just undid what I did, right? So every inverse relation can be found by switching, and then I don't really know what the heck happened here, but at each x, and because x was there, and y, it looks like my y is inside the word value, but that's the word value. So basically we switch x and y. Okay, that's something very basic that we should know about inverses for sure, right? In some situations, this process is intuitive, but other times it may not be as obvious. In these cases, it is important that we understand the concept of inverse relations, as it will help us tackle a variety of situations. So we're going to look at it numerically, graphically, and analytically, which is what we look at pretty much everything with tables, pictures, equations. So we're going to start off with the tables. So I have a table of information here. I have some x and y values. We will call this one f. We don't necessarily have to, but we'll call it that because I think we can jump ahead in some of the notation since it's not new. So when you look at this table of values, would you say this is a function or is not a function? What do we think from what we know? What's the easiest way for you to tell if something is a function or not? Is it easier from a table or from a graph, do you think? From a graph, why? What do you do on the graph? The vertical line test, right? Which some teachers call a pencil test, but most of us call the vertical line test, right? So worst case scenario, because here's what I understand from a lot of students. You know something's not supposed to repeat, but you can't always remember what's not supposed to repeat, right? My y's repeat, my x's don't. Well, I mean, you could kind of sketch it out a little bit and see, like if I plot 3, 2, let's just say this is like, if I plot 3, 2 right here, and then I plot 6, 2, that's really okay. So is it okay that my y's repeat? It's okay that my y's repeat. So this is a function. And it's, again, because the x's don't repeat, we're going to, again, formalize that language a lot here in just a minute. But it's because each x value has exactly one y value. Do I agree with that? So then if I find the inverse by switching x and y, we can call this f inverse. Again, we'll talk about the notation in a minute, but that shouldn't be brand new. So my x's become my y's, and my y's become my x's. So would you say the inverse, is that a function? No. And in our minds, it's because the x's repeat or because it fails the vertical line test, and understanding those things are important and having those thoughts are important. We are going to have to, again, formalize our language a little bit. But this is not a function because we can just say here that the x value of 2 has 2 different y values. All right, so that's not really us formalizing our language. That's still just kind of talking in terms we get. Everybody okay with that? Yes? Okay. Oh, and look at this. Hang on just a second. Well, I just realized I forgot that this happens So I've sort of given away the ending here because for whatever reason, when I erase this, now my pictures don't go away. But that's okay, because we'll get there. You only have the black lines, right? That just means I don't have to stumble through doing that again. And you are going to graph the green and purple along with me here. And we are going to start with, so if I'm going to sketch the inverse, okay, we list key points in a table. So we're going to find our key points first. And so I would say those key points will be here, 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 and here. But we're going to add one more, this one right here, the 3, 2. Okay, so add that one in there. Don't get ahead of me to the purple just yet. So, and then we'll call this one F. So for my F table, my X and Y's, I'm going to have, this is -2, -1. This is -1, 2, 2, 1, 3, 2, and 4, 3. Okay, so that is my F function. Then I'm going to make a table for my inverse. And all we're going to do in that little table is switch X and Y. So go ahead and write those out. Now for our original function, we know it's a function for 2 reasons. Well, really just one reason, because just because we have a table of values doesn't mean it actually takes care of everything. But when we look at this, it does pass the vertical line test. The reason it passes the vertical line test is because there's each X maps to a unique Y. Like that's the Y there. The X's don't repeat, basically. And so then when we go to plot these points, let's go ahead and plot these. So -1, -2, mine are already there. -2, -1, 1, 2, 2, 3, and 4, 3. Okay, don't worry about the green line there just yet, but plot your points from your second table. Are you okay? Do you need to go to the clinic or anything? You sure? Everybody got it graphed? Okay. So then it asks us, is the original relation a function? We've already decided yes, right? Is the inverse a function? No, okay? And if we look over here, the inverse does not pass the vertical line test, right? Oops, jeez. Here's the thing. When we are explaining on our FRQs, talking about the horizontal and vertical line tests, not enough, okay? Again, good that we know that, but then we have to take that and extend it to more formal wording about the concept itself. And we actually are not going to even talk about the inverse itself at all. We're just going to talk about everything in terms of F, all right? Now, when I have, so remember the function machine I showed you? We put in an X and it spit out G of X, right? So basically X is getting mapped to a value that is G of X, or an X value is getting mapped to a Y value. We've used that word before. I know that's, for some people, a strange word to hear mathematically. We're not talking about a map of the United States. We're mapping one thing to another. It's what they're connected to, all right? There are other ways to say it. However, those are the words that I'm going to use because those are I feel like we only have 4 FRQs, and there's a few things that they are very specific about how you say. And if we can just get this down and we can say it like we're really supposed to say it, it's better than just giving you the freedom to kind of say it however you want. Because then that's when y'all start to get confused about what you can and cannot say. You with me on that? Like, it's just, I don't know. It's harder, I think. All right, so here's what we're going to say. Here's the way we say it. Is that it says, is the original relation a function? So we are going to say, yes, F is a function because each input, so we're not even talking about x's and y's, we're talking about them as inputs and inputs and outputs, because they're not always x and y. Each input value is mapped to a unique output value. Okay? F is a function because each input value is mapped to a unique output value. All right. F does not have an inverse functions. Okay, I mean, it has an inverse. It doesn't have an inverse function because, all right, now we're still talking about in terms of F, all right? So each input value is mapped to a unique output value, but each output value does not come from a unique input value. You with me on that? Because look, here, my x's don't repeat. My x's repeat over here, and that's because of this right here. So when we're talking about F the whole time, it's a function because each input is mapped to a unique output. The inverse is not a function because each output is not mapped from a unique input, right? 2 came from 3 and 2 came from -1. So we're basically saying kind of the opposite of what we just said. So each input value is mapped to a unique output value. F does not have an inverse because each output value is not mapped from a unique input value. One reason why it's important to understand the concept so you can make sense of the words, all right? Each input is mapped to a unique output, right? Whatever. To a unique output value, but it does not have an inverse because each output value is not mapped from a unique input value, okay? And you don't have to circle and underline that stuff when you write it, but notice how it's kind of the same words but different. Even with all that formal language, that's not enough, okay? I went back and read the scoring reports for the FRQs. Did you see your score? Yeah. Reports and something that's called the chief reader's report. So when all is said and done and the scoring's done in the summer, the chief reader, the guy that all the questions went to about whether or not we were going to accept answers or whatever, he sits down and he writes down what they really accepted, what they didn't, why, what students struggled with, and he was very clear on this, that you cannot just talk about vertical and horizontal line tests. And even if you talk about input and output, you still have to have a specific example, okay? And all of this is coming from F. So what all this boils down to is that F of -1 equals F of 3, which equals 2. And that's why it fails. Because the output is not mapped from a unique input. It's a hot mess of words, but we are going to practice on this and we're going to make sure we understand the concept, okay? We okay with that? All right. So then something else that we've learned with inverses is that graphically they are just a reflection of each other in the line y equals x. And that's where my green line here came from. That won't disappear when I erase. It's just the parent function y equals x. And so the grid itself is not square, but if you go straight through, diagonally through the squares that go through the origin, you can sketch in in your ID makes a great straight edge. You can sketch in the line y equals x, and then you can see that. So even if, you're not going to have to graph this on the AP exam, okay? You're not going to have to do that. You are going to have to recognize whether or not they are inverses and things like that. So that is still an important concept to understand so you can recognize it. Now, if you wrote a bunch of stuff and you can't even read these words, you might need to write your answers under the lines, which is fine. But the graphs are inverses. The graphs of inverses are reflections over the line y equals x. Okay, everybody good with that? Okay, beautiful. All right, let's flip it over. All right, so now we're going to find the inverses. When I find the inverses, I'm going to switch x and y. So if I have it in function notation, I'm going to change that to a y. All right, then I'm switching x and y. So x becomes 3y minus 7. Then I solve for y without making up math. I'm going to add 7 to both sides. Then I'm going to divide both sides by 3. I have solved for y. So that's steps 1 and 2. Step 3, it was in the form of f of x, so this becomes f inverse of x, and that equals x plus 7 over 3. You do not even have to simplify it at all. Okay. Then the inverse function of f of x is written as f inverse of x. So that's your notation. It's not f to the negative 1 power. It looks like it, but it's not. Okay? We all good? All right,